This lecture is part 2 of a lecture from Section 2.3 for Math 311 linear algebra course at Western Illinois University. In this supplemental lecture, I just want to talk about there are two different ways to determine linear independence or linear dependence on vectors. And then we're going to see how this relates to some conclusions that we can make about the rows and columns of a matrix. So we're going to start off with a problem or an example that we talked about in the last lecture, and that is determining the linear independence or linear dependence of column vectors. And if we want to, we're given these three vectors, and we'd like to know, are they linearly dependent? And linear dependent means that we can find three numbers x, y, and z, not all zero, so that this linear combination is equal to the all zero vector. And of course this vector equation corresponds to a system of linear equations with three equations, three unknowns. And in fact this is a homogeneous equation because the constant term is all zero. So the augmented matrix of this system will look like this, and then we can use elementary row operations to reduce this to reduced row echelon form. And remember, the way we do that is we want the leading entry of each row to be equal to leading non-zero entry in each row to be equal to 1, and that 1 to be the only non-zero entry in its column. And we want to so we start with the leftmost column, and we want 1 up here. Probably there's a couple ways we could do this. I'm just going to interchange these two rows, and then I'm going to, this gives us a -1, and then we can multiply this top row by -1, and we get this. And then we can go about clearing out these other non-zero entries in this column. We can multiply this first row by -6 and add it to the second row, and we can multiply the first row by -2 and add it to the third row. And that's what we do right here. And then at this point we can sort of see that the second and third row are multiples of each other, but if we don't, we want to make this a 1 here, this entry a 1, so we divide by 24 for the second row, and we get this. And then we can just, then we want to make this row entry and this entry 0, which we do by multiplying the second row by +4 and add it to the first row, and multiplying the second row by -6 and adding it to the third row, which is what we do right here. And as soon as that happens, we get this in reduced row echelon form. You have to deal with a little bit of fractions here. You know, just in one of these you have to get a common denominator, but it's stuff we should know how to do. So this is reduced row echelon form, and from here we get that this tells us that 1x plus 1/3 z is equal to 0, 1y plus 5/6 z is equal to 0. So from here we get that x is -1/3 z, y is -5/6 z, and z is equal to z, meaning z can be any number we want it to be, and z in fact is going to be our free variable because here z corresponds to a non-pivot column. Right? Remember, pivots are, these ones are the pivots, and this is a non-pivot column. We talked about how the number of non-pivot columns gives us the number of free variables. So we can let z be anything we want. We could let z equal 1, but I'm going to let z equal 6 just so we can have non-integer, non-fraction solutions. And if we let z equal 6, we get x is -2, y is -5, and sure enough, these will give us our a non-trivial linear combination of these vectors. So in answer to our question, are these linearly dependent? The answer is yes. Okay. So this is stuff that we learned before. Let's try this a different way, and where we make the vectors columns, or rather rows instead of columns. So let's say we form a different matrix by having these vectors be the rows of the matrix. This technical term is this is actually the transpose of the matrix we had before, but we won't worry about this. Now, if we do this, let's reduce this, again, use elementary row operations to reduce this to reduced row echelon form. If we do that, we have, once again, we'll interchange these two, the first and the top and bottom rows here. And if we do, I'm not going to write down the operations just yet. And then we can see that we can multiply the top row by -1. We can add 2 times this row to this row, and -2 times this row to this row, and then we get this matrix, and we can sort of see that these two rows are multiples of each other. So, but we can divide this middle row by -4, and then we'll take this row and multiply it by -10 and add to this row, and we get all zeros here. And we have this in reduced row echelon form. Now, how does this help us? Well, what we're going to do is I'm going to give the rows of our original matrix a name. Okay, I'm just going to call this R1, R2, and R3. Okay, and then I'm going to, let's see, what were the operations? Well, first we interchanged the top and bottom rows. So this was R3, R2, R1. And then we multiplied the top row by -1. So this became -R3, R2, and R1. Okay. Now, what did we do on this? Well, we multiplied the top row by 2. Okay, so we got 2 times, in this case, -R3, and add to the bottom row, or the middle row, which is R2. And then we multiplied this row by -2 and added to the bottom row. So this was -2 times minus R3 plus R3. Or R1, I'm sorry, R1. Because that's the bottom row now. And then when we do that, then this becomes -R3, and this is -2R3 plus R2, and this is positive 2R3 plus R1. Okay. Now, then finally we want to make this middle row, the 1 here, so we multiplied this row by -1/4. So the top row and the bottom row stayed the same, and then we multiplied this by 1/4 or -1/4. And when you do that, this is -1/4 times -2R3 plus R2. If you do the calculations, this is going to be 1/2 R3 minus 1/4 R2. Okay. And then finally we did the operation. We multiplied this row by 2 and add to this row. So we have 2 times this 1/2 R3 minus 1/4 R2 plus minus R3. Okay, and then we calculate, well, -10 times this row is -10 times 1/2 R3 minus 1/4 R2, and we added it to 2R3 plus R1. And when the smoke cleared, what we get is -1/2 R2, 1/2 R3 minus 1/4 R2, and -3 R3 plus 5/2 R2 plus R1. Okay, if you simplify this, you get this. Now, here, because these two matrices are equal, we now see that this bottom row here has to equal the bottom row here, and the bottom row here is all zeros. So what, in fact, we get is that this has to be all the zero vector, -3 R3 plus 5/2 R2 plus R1 is equal to 0. Okay. And in fact, this tells us that negative 2, or negative 3 times negative 1, 2, 3, plus 5 halves times negative 2, 0, 4, plus 1 times 2, 6, negative 1 is equal to the 0th row. And this is the same thing as saying that negative 3 times negative 1, 2, 3, plus 5 halves, negative 2, 0, 4, plus 2, 6, negative 1 is equal to 0. But once again, we get a dependence relation on our vectors. And now notice that the coefficients here are different from the scalars we got in the previous example. But that's okay, because remember, there are infinitely many possibilities you could have for these scalars. One thing I wanted to tell you, that as soon as we're essentially done here, as soon as we got a row of zeros here, we're essentially done. Because notice that at each step, the rows of each matrix in this process are linear combinations of R1 and R2 and R3. So as soon as we get a row of zeros, we get that there's some linear combination of R1, R2, and R3 is equal to 0. So really, we could just do this, and as soon as we get this row of zeros here, we can stop. Okay. All right. So let's just summarize what we've learned about these two ways to do this problem. So if we do this by column vectors, again, we just set this up. If we're given column vectors, we can set them up and form a matrix A. And then what happens is we have the following, our equivalent. We say these vectors are linearly dependent if and only if this system of linear equations given by this augmented matrix has a non-trivial solution. And that happens if and only if the reduced row echelon form of A has at least one non-pivot column. Okay, and again, the reason for that is the number of non-pivot columns equal the number of free variables and the number of, and then free variables imply infinitely many solutions. And of course that implies a non-trivial solution. Okay? All right, so we won't go through the proof of this again, but that's why this works. So that's happened if we're given column vectors, or if we're just given vectors and we want to make them columns of a matrix. Now the other way that we just did can be reflected in this theorem, and that says if v1 through vn are vectors, are row vectors now, and we take A to be the matrix having these vectors as its rows, then the following are equivalent. Okay, and again, equivalent means that if one statement is true, then all of them are true. First says that these, again, the vectors are linearly dependent. The reduced row echelon form of A has at least one non-zero row, and the rank of A is less than n. B and C are equivalent just from the definition of rank. Remember that we define the rank of A to be the number of non-zero rows, not the number of non-zero rows in its reduced row echelon form. So if the rank of A is less than n, and we have n rows, well, one of those rows has to be non-zero. It has to be all zero, right? Okay. So then that implies B. Okay, and similarly, B implies C just from the definition. So B and C are basically the same statement. We already showed that if the reduced row echelon form has at least one non-zero row, that these are linearly dependent. We talked about that because that zero row is going to be a linear combination of the rows of this, which are just the V's. And then the only other thing we have to show is, well, if they're linearly dependent, that means the reduced row echelon form has at least one zero row. And the reason for that is as follows. Okay, to show that A implies B, okay, if they're linearly dependent, then we can find vectors C1, V1, through C, and Vn. We know that's 0, okay, where not all of the C's are going to be 0. So let's assume that Cn is not 0. So then Cn Vn can be written as minus C1 V1 dot 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 plus minus Cn minus 1 Vn minus 1. And we can divide both sides by Cn since it's not 0, and we get that Vn is going to be minus C1 over Cn V1 plus minus Cn minus 1 Cn Vn minus 1. Okay, so Vn is a linear combination of these others, and we can give these fractions a name. We'll say Vn is, we'll call this number, we'll just call it D1 V1. And this is Dn minus 1 Vn minus 1 here. Okay, and then now A is going to be V1 through Vn minus 1, and then the last row is going to be D1 V1 plus D2 V2, so on Dn minus 1 Vn minus 1. Okay, and then we can do a series of row operations where we can multiply the first row by negative D1 and add it to the last row. We can multiply D2 R2 plus Rn minus Dn minus 1 Rn minus 1 plus Rn. And if we do all that, then all these are going to be canceled out, and what we'll get is V1 through Vn minus 1. Then we'll have all zeros here in the last row. Okay, so we will have, all right, and then we can proceed. Any further row operations will only affect these upper rows. So we'll have this row of zeros will be there in the reduced row echelon form. Okay, so that implies that we have at least one 0 row. Now, a nice little corollary of this, or a direct consequence of this, is that any set of m vectors in Rn is always going to be linearly dependent as long as m is bigger than n. And the reason for that is the following, is that if we have the rank, if we have V1 through Vm here, we can see that the rank of this matrix A is going to be is always going to be less than the number of rows. It's going to be the number of rows, right? Okay, so yeah. Okay, so that from there, let me just see if m is greater than n, right? So, right. So we're going to have to. Then that means that we're going to. We're going to see that we're going to have a row of zeros here. Because we're going to, the reason for that is because there are just so many more vectors here. The maximum number of pivots you can get is just equal to the number of columns, which is n, and that's less than m. Okay, so we can't. It's impossible to have m pivots. All right, so we're guaranteed to have a row of zeros here, and it's reduced row echelon form, and that's why it's linearly dependent. Okay, all right. So thank you for listening, and we'll see you next time.